All right, today we are going to continue with some more vocabulary for graph theory. Last class, we looked at some of the basic vocabulary like vertex and edge and loop. Today we're going to get into some more advanced vocabulary. So you can see this graph here. This is the graph that we are going to use for the next several slides as we go through some of these vocabulary words. So our first term that we're going to look at is adjacent vertices. Two vertices are said to be adjacent if there is an edge joining them. So, for example, A and B would be adjacent vertices because there is an edge from A to B. D and E would be adjacent vertices because there is an edge connecting D and E. C and D are not adjacent vertices because there is not an edge from C to D. Similarly, A and G are not adjacent vertices because there is no edge directly connecting A to G. Adjacent edges are two edges are adjacent if they share a common vertex. So for example, AB and AC are considered adjacent edges because they share vertex A. GF and HF are also adjacent vertices because they share vertex F. However, DE and AB are not adjacent vertices because they do not have any, or adjacent edges, because they do not have any vertices in common. All right, again, continuing with the same diagram. So we are going to look at what is called the degree of the vertex. This is a very important concept, but it is pretty simple. The degree of a vertex is just the number of edges at that vertex. So if there's a loop, you count both ends of the loop. So we're going to go through and write the degree of each vertex in this diagram. So at A here, I know this diagram isn't perfect, but there are 3 edges that come into vertex A. So the degree of A is 3. Vertex B, we have 1, 2, 3, 4, 5 edges. Vertex C, we have 1, 2, 3 edges. Vertex D, we have 1, 2. Vertex E, this is where we mentioned the loop. We have 1, 2, and then both ends of the loop. So we have 4 edges coming into vertex E, so our degree is 4. Vertex F, we have 1, 2, 3 edges. Vertex G only has 1 edge, and vertex H has 1 edge. So those are the degrees of all of the vertices. Now, we can categorize them into odd and even vertices. An odd vertex simply has an odd degree. An even vertex has an even degree. So how many even vertices do we have? Well, that would just be D and E. So we have 2 even vertices and 1, 2, 3, 4, 5, 6 odd vertices. Okay, this would be D and E, and this would be all of the others. All right, continuing with our vocabulary. Same diagram. Now we're going to look at paths and circuits. A path is a sequence of vertices with the property that each vertex in the sequence is adjacent to the next one. The number of edges in the path is called the length of the path. So, for example, I could create a path from A to E that goes A, D, E. That is an example of a path, and the length is 2, because it took us 2 edges to get from A to E. Now, an example that is not a path. Okay, if we are looking at B to G, BG is not a path. But BFG is. All right, and a circuit is a path that starts and ends on the same vertex. So, for example, if I go A, B, C, A, that is an example of a circuit. And we can also talk about the length of the circuit as well. In this case, the length would be 3. Okay, but G, F, H is not a circuit. That is just a path. All right, let's look at a few more vocabulary words. So, connected and disconnected graphs. A connected graph. A graph is connected if, given any 2 vertices, there is a path joining them. A graph that is not connected is said to be disconnected. A disconnected graph is made up of separate connected components. So this graph is connected. And here we have some examples of disconnected graphs. Okay, this graph here, we have component 1 and component 2. Okay, there are 2 separate pieces to this graph because, for example, there is no path from this vertex to this vertex. This is also a disconnected graph. It is 4 vertices and no edges. So this actually has 4 components. Okay. So we have 4 separate pieces to that graph. All right. And then the last vocabulary word on this page is a bridge. A bridge is when if you erase an edge in a connected graph, the graph becomes disconnected. So that edge that you erased would be a bridge. So looking here, what edge could we erase and make this a disconnected graph? Well, there are actually a few bridges. We have GF, where if we erase this edge, G would become an isolated point. Same thing with HF. If we erase that edge, H would become a disconnected or an isolated point. And then BF, if we erased this, then GFH would be disconnected from the rest of the graph. So we have 3 bridges here: GF, HF, and BF. Those are our bridges. So now getting to the most important part of this unit, an Euler path. An Euler path is a path that passes through every edge of the graph. Edges can only be traveled once. So in an Euler path, you travel each edge of the graph exactly once. A disconnected graph cannot have an Euler path. And only some connected graphs have Euler paths. We will talk about which graphs have Euler paths in the next video. But I will just tell you now, this first diagram, which is actually the Bridges of Königsberg diagram, does not have an Euler path, but this one does have several Euler paths. Similarly, we can have Euler circuits. An Euler circuit is a circuit that passes through every edge of the graph exactly once and starts and ends at the same vertex. Again, we will talk about what graphs have Euler circuits in the next video. But this graph does have several Euler circuits. You can play around and see if you can find one. So, what is the point of all of this? Well, as I mentioned in the previous video, one of the cool things about graph theory is that you can take a real-life situation, model that situation with a graph, use the principles of graph theory to find a solution, and then translate it back into graph theory or into real life. So, 2 examples here. After a rash of burglaries, a private security guard is hired to patrol the streets of the Sunnyside neighborhood. The security guard's assignment is to make an exhaustive patrol on foot through the entire neighborhood. Obviously, he doesn't want to walk any more than what is necessary. His starting point is the southeast corner across from the school, and that's where he parks his car, and he wants to find an Euler circuit through the neighborhood. So we can take this map of Sunnyside, change it into a graph. All of the intersections are the vertices. Each of the roads or sidewalks is an edge. And we could use graph theory stuff, which we'll learn in the next video, to figure out how to come up with an Euler circuit through this neighborhood, where he starts and ends at his car. Also in Sunnyside, if we're looking at the mailman or woman, the mail carrier has to deliver mail to the same Sunnyside neighborhood, but the difference is that the mail carrier has to walk on both sides of the street so that they can visit all of the houses. But the security guard just really needs to walk down the street once and check and make sure nothing looks suspicious. So, again, we can use multiple edges on the same map to represent the area that this mail carrier needs to walk. You can also see the mail carrier does not need to walk around the school or around the park because there aren't houses there. So we can use this graph, try to find an Euler circuit from P, the post office, around the neighborhood. And that is it for today. In the next video, we will take a look at how to find Euler paths and circuits.